So we're going to skip these slides because they talk about how the book builds their own graph data type. But we're going to use our own in just a couple videos to see how this works. So instead, what we're going to do is that we're going to just talk about the generalized ways we implement them. Okay, because there's two common ways to implement a graph, which is the adjacency list, where we have a list, or a map would actually be way more efficient, of vertices adjacent to a particular index. So in other words, right, in a map, we would use the categorization, right? So the key would be the vertice we want to store, and the value. So the key, vertice, the value would be the list of all vertices that it's adjacent to. That's one way to represent a graph, which is to keep track of these adjacency lists. So for every graph, we would keep track, for every node, we would have that node as a key, and the value would be all the nodes it's adjacent to. The other way to represent it is that we can represent it in a two-dimensional array. And right, this is about dealing with simple graphs. And we can use a two-dimensional array called an adjacency matrix, and we basically use each cell in the adjacency matrix to represent whether or not there's an edge there. Interestingly enough, how to implement graphs in computers, figuring that out came well after the publication of many graph problems, because graph theory, again, this came about as it really got its foundation started in 1736. So it took a while for basically using computers on graph problems. So the how to build these data structures was a much less important issue at that time until we had to implement them. So again, adjacency list is a representation of they use an array of lists, one list for each vertice. Like let's say the vertices are numbers. The way we can represent this is that we have our vertices 0, 1, 2, 3, 4, 5, right? So we have a list at index 0 that's going to hold a list of all the nodes I'm adjacent to, right? So 0 holds 1 and 3, right? Because I can get to 1 and 3. 1 holds 4 because I can get to 4. 2 holds 4 and 5 because we can get to 4 and 5, and the order there doesn't matter. Okay, interestingly enough, we've got this self-directional edge over here. That's completely legal in a simple graph, right? You can have something can have a relationship to itself, right? So we can get from 5 to 5 from there. And this is a directed graph example, right? An undirected graph, that might look something like this, right? We can get from 0 stores 1 and 4 because you can get to 1 and 4, and 1 stores 0, 4, 3, 2 because those are the ones it's adjacent to, right? So for every node we have a list. Or it might be or more realistically, it might be something like a graph. You might store it in a map that might look like this, right? So map adjacency list, and what would that look like? It would look like let V be the type for vertices, and let's say it's a list of these, right? So it would be V, the vertice, and then the list of V's over here. That way you can do any type of vertice, not just integers. All right, so that's one way to do it. The other way is an adjacency matrix, which is a two-dimensional array used to represent the graph. So unweighted graphs, this is a fairly straightforward way of doing it. We can use it can be a 2D array of booleans or 2D arrays of integers, right? True or 1 for an edge, or false or 0 if there's no edge. Integer, we prefer to run with integers, though, because you can do matrix multiplication then, which is pretty fun there. So let's go ahead and take a look at kind of just an example graph there. Right, so let's go ahead and look at an example graph and example matrix. All right, so let's look at so I'm going to use only 4 items, right? And we're going to do this in reverse. I'm going to say we have A, B, C, D, A, B, C, D. So I'm going to draw my matrix over here, and then I'm going to draw the graph from it. Okay, so let's go ahead and say we've got a edge here, 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 and here. Right, so I needed to, let's see, so let's get our graph here. We have A, B, C, and D, right? And we'll fill these in with zeros for everything else. Okay. So first, A doesn't have an edge from A to A, but it has edges from B, C, and D. B, C, and D. B has no edges so again, this is a directed graph over here because while A has an edge to B, B doesn't have an edge to A. C has an edge to B. And D has an edge to D. Okay. So that's kind of the way that would work. So for weighted graphs, what we would do is that we would contain weights. However, we run into so for a weighted graph, these values, rather than holding zeros and ones, they would have an actual number that would be the weight. But 0 is a valid weight. So instead what we do is that we use positive infinity to represent the weight. Oh, a 0 is a valid weight? Well, let's go ahead and take a look at another example, right, where that might be, right? Suppose we have the Benjamin Franklin Bridge, right, from Philadelphia to Camden, right? Well, it costs no money to get to Camden, right? It costs $5 to get back from Camden to Philadelphia. So that's an example of 0 being a valid weight in a directed graph. So, so an unweighted graph, we could also just use 1 for a presence of an edge. So here are 2 examples you can look at. And for an undirected graph, if we wanted to be smart about it, we could just store the lower triangular because it would be reflexive. But here's 2 examples of that.